I'm going to be now focusing. I'll mostly spend most of the time on the basics, on the infrastructure and everything, and it's only at the very end that I will show anything 3D, which is what I'm currently working on. But still, it's good, I think, this way, because then we can get to understand what's the whole thing that is behind the latest efforts and results. So yes, and also to locate where this work really is within the bigger picture, going from full theory on top all the way to observations at the bottom, going through all of the intermediate steps what one could have. This talk is going to be related to the part here, numerical relativity, where we take the Einstein equations from general relativity, discretize them and solve them numerically on supercomputers so that we can obtain gravitational waveforms, make waveform models, and then use those to compare to the data that comes from the gravitational wave interferometers. And using this analysis, we can understand if GI is correct or not, implications about cosmology and on astrophysics. And when I say here general relativity, you could just put your favorite modified theory of gravity. However, I mean, general relativity is still the one which is the more mature at the level at which we understood it, and at the level that we can actually make numerical predictions from it. But yeah, that's what I'm going to be focusing on now. And so within this I'm going to now talk about simulations of binary systems, be it neutron stars or black holes, and I'm going to mostly focus on black holes because they're simpler and there is less physics involved in a way. And what we can do indeed, and we are doing, is simulating these binary systems of compact objects. But still, we know that these simulations, we have heard these simulations take a long time to be performed, and we would like to make them more efficient. We are indeed extracting the gravitational wave signals that these systems emit during the spiral, the merger, and the ring down. But we need better accuracy in the signals that we extract, because as we know, third generation detectors and LIS are going to come online at some point in the next decade, and we will need models and thus waveforms which are accurate enough for those requirements. Then what many numerical codes do is they extract signals at a finite value of the radial coordinate when they're in the simulations. And then they propagate the extracted waveforms all the way to infinity, which is the only location where they're actually unambiguously defined. However, we would like to be able to directly extract those signals at infinity. And I'm going to say something more in the next slide on that. And something rather complicated that numerical relativity codes have, and other codes in other areas of physics, is boundary conditions. So how do you impose conditions? You need to let your signals go out, but also account for what should be coming in. And that is something difficult to deal with. Can we do that without any complicated constructions? And I'm going to try to convince you that there is an approach that can solve most of these problems, if not all, and that is the hyperboloidal approach, which some of you may already have heard about. Now,
Alex, can I ask
yes, of course.
My general question?
Yes.
When people compare to LIGO interferometer things, the waveforms, that's always from numerical relativity. The theoretical ones.
Well, so if you want a signal that goes through merger, then only numerical relativity can give you all the information you need. If you just focus on the spiral part, then you can use post-Newtonian methods or something similar that can give you that bit. But once you get in the full nonlinear regime, you need to know numerical. So, but indeed, something about that, how numerical relativity simulations are expensive. So what people normally do is they just make about 10 orbits in numerical relativity, and then they hybridize them with a post-Newtonian in spiral waveforms with everything together, so they have a longer signal. That's one way of doing it. So yeah, this hyperboloidal approach. And now I said infinity, and I'm going to focus on a very specific infinity, which is functional infinity, also called square plus, and that corresponds to the endpoints of feature-directed null geodesics. It's located here in this compactified diagram of Minkowski spacetime. And it is relevant because it is only at infinity that we can study certain global properties of spacetime, such as the mass or the energy contained in the system. And it's also where gravitational waves, because they travel at the speed of light, where they can be measured within the spacetime. Also, they correspond to the correct idealization of us observers of astrophysical events, such as we here on Earth with our interferometers. And it's also at feature infinity that we can measure the gravitational wave memory of that. And how can we get there if it's infinitely far away? Well, what we may get there is include infinity in our numerical domain. So this is infinitely far away, so our coordinates are going to blow up there. But however, our fields decay. So if we balance both effects properly, we will be able to have something we can work on. And an example, that's the one I'm going to mostly focus on in this talk, is based on Penrose's conformal compactification from the 60s. And then let's see, how do we set up a numerical simulation? So what you need, what we usually do is we express the Einstein equations as an initial value formulation. That is, we just give initial data on some slice we choose, and then use the Einstein equations to evolve that on time. How can, so again, this is the initial data we give here, and then we use our Einstein equations to tell us what the solution is here. And I'm just in blue, I'm putting these two quantities. In blue, the alpha is the lapse that controls this, how far away one slice is to the next, and the shift that controls the change of coordinates from one to the next. This is something that we choose, and I'm mentioning this because these are the gauge quantities, and I'm going to talk about gauge conditions later. Just that's something, some freedom we have in our field. And now, what kind of slices can we slice our space, and just use to evolve the Einstein equation of? So the simplest are usual standard Cauchy slicing, which are spacelike, like the red ones. And as we have finite resources, we usually just cut at some value of the radial coordinates, such as the dotted line here, and evolve what's inside. However, if you want to get to infinity, we need to have a full slice. But standard Cauchy slices, they do not reach frictional infinity, they only reach spatial infinity, and that's not where we want to go. The simplest way to actually reach frictional infinity is via outgoing null characteristic slices. And while that is indeed doable, one of the drawbacks of this approach is that so if the generators of these null slices become tangent to each other, that's when posticks appear, and that basically means a breakdown of the coordinate system, and this can give trouble at the numerical level. And this can happen due to the focalizing, due to the strong field path, as we're going to have black holes and neutron stars. We could take the best of both worlds, and inside use standard Cauchy slices, and at some point match them to outer characteristic ones. So the matching path would be give data on the whole bit and evolve forwards. Has some problems in the sense that one has to be very careful in the way we just choose both formulations, because the way of solving the Einstein equations here and here is not the same. That's tricky and it's being worked on. Extraction means that we evolve what's inside, and then extraction or evolution, and then evolve with the system all the way up to scribe. There's codes that actually do that, one CCE by the SXS collaboration, and that is indeed working, and that will get you to signal at frictional infinity.
How do you match? How do you match?
Well, I'm not an expert on this. So if you talk about the actual matching, the tricky part is that you're using different formulations and different gauge conditions, and they have to go well together. And it was found actually by work by Thanasis Giannakopoulos here and David Hilditch and his collaborators, that the formulation normally used for the characteristic part is not well posed. So that means that the whole system is not compatible, is not going to be stable if you try to solve it numerically. I mean, more details I do not really know. It's not easy. Yeah, so that is why what we're trying to do is to solve using something intermediate and smooth, which would be these hyperboloidal slices, the green ones here. That, as you can already see, they are smooth everywhere. They are space-like, although asymptotically they reach fictional infinity. And for the construction, if we compactify on them, we will already give more resolution to the central part where the actual dynamics will take place, and the wave zone far away has less grid points, so it's going to be more efficient. That's what we expect. Yes.
They are looking the waveforms, for instance, like
No, because they use CCEs, so Cauchy characteristic extraction. In that case, you evolve in here, and then you just use your I don't know exactly what the formulations that they use, but that is fine because they just take it from the inside and pull it out to the outside. Whereas the matching bit, you evolve everything at the same time, and that's more difficult in that respect. And they have like this Cauchy characteristic extraction code that you can actually also use for data that you have already from your code. It's actually quite nice. It's a standalone thing. Yeah. So that's fine. And now I wanted to give you a taste of how this can look like. So here, what you see is, so there's many lines. I would like you to focus on this purple one here, the smaller one. That is a scalar field perturbation on Minkowski. So all of these quantities are metric components. This is a simulation in spherical symmetry. And the relevant bit is that here at the origin, you have the origin of your coordinate system, and at r equals 1, you have functional infinity. So all the way to here, on one of those green slices. And let me know, just pay attention to the behavior of this smaller, of this smaller. So it's moving in here. Actually, part of it has already left. Now it's going back to the other way, and it's just going to leave here with this functional infinity. So whatever perturbation we had has been reflected at the origin, and then moves back and leaves the domain in functional infinity. And in the end, we have just Minkowski empty space, nothing happening there. And so we can see a bit more the behavior of the scalar field. And let me say that here it's a scalar field coupled to the Einstein equation, so it's full GR. Yeah. And so now let's look at just the part that corresponds to the scalar field. This is the initial perturbation. It has split into two parts. One of them here propagates all the way towards functional infinity, which is here at equals 1. The other one goes towards the origin, is reflected, and again goes back and leaves the domain through functional infinity, which is here. And here we see the signal that we would see at functional infinity as a standard as well. And that's that. And something relevant is that the speed of the propagating fields, which travel at the speed of light, is finite in functional infinity. So this is reached at a finite time, and numerically it works well. And now, if this work, so Penrose's idea was in the 60s, then in the 70s, Helmut Friedrich took it and applied it to the Einstein equations, and then he showed that it was possible to obtain regular equations with that approach to solve these type of problems. And the first numerical implementations happened in the 90s with a seminal work by Anil Zenginoglu in the 2010, yeah. So it's now 2022. Why is it taking so long to actually get this to work, which is not really working just yet? So the main difficulties, at least from my experience, are that either your evolution variables or your equations are going to be diverging at functional infinity, because it's infinite far away. I mean, you can use many tricks, but still you have to deal with it. And that's something we need to balance, and it is not a straightforward thing to do. So either we need to rescale our quantities so that everything is as using their decay, so that everything is as regular as possible at infinity, or we need to make sure that terms on the Einstein equations that are formally singular cancel up with each other, and this requires some work. And on top of that, the background that we have, which is that asymptotically the trace of the extrinsic curvature, which is usually 0 for Cauchy slices, standard space-like slices, it is not 0 in this case. It's a non-zero value, and that gives us a non-trivial background that we have to deal with our gauge conditions, which is a choice we put into how we solve the equations. And this talk, I'm I'm presenting now shows the first pre-evolution of a hyperboloidal implementation that uses a common formulation, such as BSSN or Z4, which is commonly used with the moving puncture approach for big binary black hole simulations, or the generalized harmonic gauge using the dual frame approach. I will talk about this a bit later on, which is commonly used with the excision way of treating the black holes in big binary black hole simulations. So now let me focus. I'm going to be mostly talking about this approach now because it's the one I've been working on the most. And then I will say something about this before I showed you the current attempts at 3D simulations. So conformal compactification based on Penrose's idea, which is the following. Instead of working with our physical metric, which will become infinite at infinity if we compactify our coordinates, we multiply it by a conformal factor, which is chosen in such a way that it goes to 0 at fictional infinity, so that this rescaled metric is finite everywhere. And now we can express the Einstein equations in terms of this rescaled metric. And this is the way. So everything here is going to be finite. If the energy momentum contained in the system decays fast enough, this will be fine, okay, as well. But here we have to obtain these three terms that are formally singular at fictional infinity because omega goes to 0. And now the tricky thing is that we have to ensure that these terms, they should, but things are not so easy once you get onto the code. And now I'm going to basically cover the main steps of the implementation, showing the formulation of the evolution equations that we use. Then I will say a few things about the type of initial data that we can give for these hyperboloidal slices. Then I will mention a few rather important bits about our choice of gauge conditions and about the numerical implementation. I'm going to say this, which is we use the method of lines with finite differences for the spatial derivatives in the equations, and then we will put a 4 for the time integration together with price-solid dissipation to keep things stable, or to help keep things stable. But let's go into the equations first. So this is our line element. So this is with the lapse and the shift going to the game. This is the spatial part of the metric in this spatial conformal factor. And so as it was not so long ago, it was Halloween. Let me scale you a bit with some equations. So here you can see these are the evolution equations for these quantities. And I'm showing them here because, as you can see, there's a few terms, quite a few terms that actually are formally singular at fictional infinity. And we have these will have to behave well numerically speaking. So this for that, and then also this for the two remaining evolution equations and for the constraint equations. So yeah, that's just there's not going to be any more equations this long again. This is what we put into the code, basically. Now, what data do we feed to those equations? The way to obtain, or one way to obtain initial data on hyperboloidal slices consists of taking your chosen line element, or here this is for Minkowski spacetime, and then you perform first a time a transformation in your time coordinate. So the old time is related to the new hyperboloidal time by a height function. And this height function, its job is to actually raise the slices so that from a usual space-like slice like this one, you go up to here, up to fictional infinity. And the job is done by this height function, which for Minkowski spacetime, you can choose it to be this, or you can choose it to be something else. And then once we are on this slice, still our radial coordinate is still infinite. So then we perform a compactification, and we just choose our compactified radial coordinate to be actually, so the non-compactified is the compactified over something that goes like omega at close to square plus. And usually for Minkowski, it's useful to choose that to be basically, this would be 1, this is a constant, so it's basically proportional to 1 minus r squared, where 1 is where r squared is. If you do this, then you can just make this plot. Well, actually, you don't need this part to make those plots because the way you compactify is different. But with these two ingredients, you can give data on a hyperboloidal slice, and that you can feed into your equations. And now let me show you a simulation which is similar to what we had before. It's a bit different in the sense that now this scalar field is bringing more energy to the system. And let's see what happens. So this is again, the scalar field is in purple here. And I will also ask you to pay attention to the blue line, which is the lapse. And let's see what happens close to the origin. So the scalar field, one bit has left through fictional infinity, and the other one is going towards the origin. And the relevant bit, the difference with respect to the previous animation is that in this case, here we have seen this is the appearance of an apparent horizon because the energy of the scalar field has collapsed to a black hole. And this corresponds now to a black hole. Just to give you an impression of how this could look like on a Penrose diagram, the initial data is on one such slice, more or less. This is not numerical, but just to give you the idea. And then the final one would be after the collapse has already happened. So something which has a horizon and corresponds to a trumpet geometry. And into that trumpet geometry, this is one possible way of dealing with singularities in the theory and also various numerical simulations. So you want to avoid the Schwarzschild radius equals 0. Now I'm focusing on Schwarzschild. And the common way to do it is to choose a wormhole slice like this, so that we avoid this bit here. Now, what happens if you give this initial data with the moving puncture gauge and let it evolve numerically? So what will happen is that the initial data here is going to move up in time. So this is the time equals 0, then we get this data is here, then here, then here. And if you pay attention to this bit here, you see how we are losing resolution in this asymptotically flat end. So towards the end of the simulation, the data we have is actually like this. And this gets very close to this type of slice, which is different. It also avoids the singularity, because what happens is there's an innermost value of the Schwarzschild coordinate that you can reach, and then your proper length becomes infinite. So this would be the corresponding embedding diagram of this trumpet slice, this trumpet geometry. And so the codes deal well with this type of slices, and that's also does the approach I'm taking with the hyperboloidal. So I can, this is just a regular trumpet, not hyperboloidal, but here you can see an example of a slice which is hyperboloidal in the sense that it reaches fictional infinity, and on the other side, it avoids singularity by going all the way to here. And this, I can just give initial data there, feed it to my variables, and everything is fine, is smooth everywhere. That's the approach of using this trumpet hyperboloidal slices. CMC stands for constant mean curvature, which is one way of giving this data. Right. One thing I want to mention about this type of initial data is that if I just give this initial data, this is just a CMC trumpet, CMC Schwarzschild trumpet, and just let my my simulation evolve with my choice of gauge conditions, I'm going to talk about in the next bit. This is what happens. So you think something's going on, and at some point the simulation stops. No physics is happening here. This is just gauge dynamics. Just the trumpet is slightly moving a bit. So what if you were to look at this in, good, I hope it was, okay. I see. Let me do something first, please. There we go. So if we were to look at this evolution in Penrose diagram, so these are the same, this trumpet, hyperboloidal trumpets I was showing before. This is the way it evolves. So they move up because they move forward in time, and it becomes less and less points in here because actually the gauge is the shift's actually just getting the points out of the horizon. That's why it's looking like this. But the relevant bit is that, there we go. The initial that I'm giving are the black lines, and after evolution with these gauge conditions, I get the blue lines. This is fine. Nothing is really happening. It's just a change in the slides, but I would really like to understand it better. And that is due to the effect of the gauge conditions. And to talk about those, now let me say first, I talked at the very beginning about boundary conditions. And I said it's something very tricky to solve. Now, the good thing about functional infinity, and an asymptotically flat spacetime, is that it is an ingoing null surface. So that no information, it's the opposite of a horizon, no information is allowed to go in. So that I do not need to account for any incoming waves or any incoming information. I just need to leave, to let whatever is propagating to square, to just let it leave the domain, and it will all be fine. That's why what we want is to ascribe at the limit of our numerical simulation, of a numerical domain, so that we don't need to impose boundary conditions. And that we do by making the time vector flow along fictional infinity. That's achieved with the shift vector basically. And on top of that, I need to specify how my lapse and my shift behave in time. We need this to complement the evolution of the Einstein equations. And these are the choices that I make for the spherically symmetric simulations. This is a type of Bonnet-Masson equations generalized with some extra terms that I need for them to adapt to the hyperboloidal slices. And something similar for the gamma driver shift condition, which has this form, and I can add some extra terms if need be. And then this slide here is a bit technical, but the concept's actually relevant. So we want that when we go to fictional infinity, that the time there that we are, ideally we want the time that flows there for us is the bonded time. That corresponds to the time, the proper time of inertial observers moving along fictional infinity. Because what can happen, now we're going to focus on the signal here. If I perform the same simulation with different choices of gauge conditions, like the ones I showed before, I may get different curves for the exact same initial data, because we're just choosing different gauge conditions. But which of them is the right one? Like which of them is going to give us the signal which is not deformed for whatever behavior of my gauge conditions? But the one that corresponds to the bonded time, and the one with the bonded time is the one in black. It's actually behind many of them over here. And ideally, we want to be able to evolve with the bonded time. If that is not possible at the numerical level, within the code as with the simulation, then we need to be able to recover that. And that we do by taking all these things. And now, before I show you the first attempts at spherical symmetry with this conformal approach, I would like to mention a few bits about the dual frame approach, which is the one being led here by David Hilditch, also with Edgar and several of the PhD students working with him, also aiming to solve the hyperboloidal problem. The difference is that here we use, you need two sets of tensor bases. One, the capital, one with the capital coordinates actually are used to express the equations and ensure that they are hyperbolic, which is something you require for any numerical implementation. And then you have another set of coordinates, the lowercase ones, which are adapted to the geometry of interest. So this one are used to express the Einstein equations in generalized harmonic form, and these ones will be adapted to the hyperboloidal slices. That is the basis. And instead of using conformal compactification, as I mentioned, we're scaling the metric by this omega factor. Then here there's a more careful understanding of the decay of each of the evolution variables, so that everything is regular at scribe and the equations are as regular as possible. Now, this is an ongoing implementation, so that's in spherical symmetry, but we also study these things in 3D, so that some of the students here have presented in other instances. So these are the choice of variables made for the metric. It's not the lapse and the shift that I was shown before. It's more sophisticated. It looks more complicated, but it's because those are the quantities that have a very well understood asymptotic behavior at functional infinity. And you can write the Einstein equations in spherical symmetry in terms of those quantities. They are made very compact, so they look very nice, unlike the ones I showed before. But in the end, the content is the same. And now I would like to show you a movie from some time ago of the implementation of the previous equations. These are constraint violating initial data, but the aim of this is to show how things how nice they look at fictional infinity, which is again at I equals 1 here. These are just some of the evolution quantities. So as you see, everything goes out very nicely. And I would like now to show you an example of, well, these are the signals there. This is what if you were to be sitting at square class, you would see this. Maybe different colors, but you see the same thing. And this is just a convergence test. You cannot talk on some numerical methods or code if you don't show any convergence test. It's a requirement. So a convergence test is what you perform in order to be able to ensure that your data is reliable, in the sense that as you increase your resolution, your solution has to get closer to the real solution, which you usually don't know because that's why you're solving numerically, because it's no analytical expression for that. And that means that the differences between high and high resolutions become smaller and smaller and smaller. And that's a special rescaling. And if you use that rescaling for your data, then you should be able to get curves that coincide. And if they coincide, means it is converging. And it is indeed very good convergence at fictional infinity, which is a really good result. And now I would like, this is going to be the last bit of the talk. I'm going to show what I'm currently doing with the conformally compactified approach onto 3D. Before I started with the Einstein equations, I considered the scalar field evolving on a 3D hyperboloidal slice. So what you see here, oh yes, and I forgot to say, this is the massless wave equation, and this is evolved within a code infrastructure called NURPy. It has several Python scripts that generate C code. That's what actually runs. And what you can see here is that from the center all the way to here, that's the radial coordinate. So that this would correspond to scribe, to fictional infinity. And then this is for a specific value of the theta coordinate, because this is in full 3D. And this corresponds to the phi coordinate. So just specifically theta. And this is the initial perturbation, well, the initial value of the scalar field, and I will see how that evolves on a Minkowski hyperboloidal background. Yeah, so the initial perturbation just moves around a bit, is reflected, and leaves the remain to scribe. Nothing else happens. This is just the wave equation being applied. And this is pretty much the same, only not spherically symmetric, so the dynamic is a bit richer, a bit more interesting, but in the end the same thing happens. Perturbation goes away, Minkowski is left. And what I'm doing, well, I spent some time in Summer at Perimeter Institute working with Eric Schnetter to try to do the same thing, but within the Einstein toolkit, which is a much more powerful code. So that's something which is ongoing. But now I would like to focus on what I've been doing with the Einstein equations in 3D. So this is some perturbation on the lapse quantity. And this, if I run it, this is also in full 3D. If I run it, it doesn't look like anything very special. This is just a perturbation, but if you look at how that affects, for instance, this variable, which is one of the quantities that you evolve in those equations, it will have quite an impact. And you see how this is propagating. And here again, this is the origin, and this is scribe. And I will run this again so you can see that this is fully, there's no spherical symmetry at all. So the behavior at scribe is wobbling differently depending on the direction. And yes, just to keep this stable is already quite a big, I consider it's a rather big achievement, because it's like making sure that all these flows ups and decays are kept balanced. And so then this is showing that it mostly works, but not quite, and that's what I'm doing right now. This is a convergence of one of the constraints. So the constraints in pre-evolution, they have to be satisfied initially, and that ensures that they will continue to be satisfied later on in time. So, and you can also rescale them so that you can check convergence. As we're going to see here, initially, inside convergence was good, but now it has gone bad. And whatever was making it bad has come from fictional infinity here. I'll run it again. So this is very good. They coincide, but at some point it stops being like this. And that's because of something bad that is happening at fictional infinity. So it means that even if the code is stable and it seems to be promising, there are still things to be solved. And that's actually what I'm doing right now, like 1 hour before. So yes, and then I would just like to, with this, conclude with a little summary. So let's not forget that all this work is being done because we want to be able to have better waveforms. And in order to do that, we want to be able to do binary systems, and at the same time extract the corresponding gravitational wave signals at functional infinity. And this is a very promising way to do that. That's why we're spending so much time and effort on this. So in terms of the conformal compactification approach I spoke, which is my main project, there's some bits to still be understood in spherical symmetry about the relation between those gauge conditions and the black hole trumpet geometry. And I'm currently doing all these robustness and convergence tests in 3D in NLP. And for that, this is just Minkowski so far, but I need to also include gravitational waves. In 3D, you can have gravitational waves propagating, and for that, I'll also need to get initial data that has that type of initial. So the constraints satisfying that type of initial data. And then I will consider including black holes as well. So, first one black hole, one third black hole, and see, and at some point put a binary in. There's some work in the past being done, so everything has to be put together. And once all that is done, then following the example of the wave equation, they use that in the Einstein toolkit, which is a much more widely used and powerful numerical infrastructure. And with respect to dual frame approach, several people in here are working on this. So one way is to add in spherical symmetry to add a scalar field for some interesting simulations, and also include in black hole initial data using excitation that is taking away everything which is inside of the horizon, and work towards evolving the linearized Einstein equations in generalized harmonic form in 3D is already being worked on. And just to finish, let me make some advertising. There's a website, hyperboloid.al website, where it's still under construction. There's not a lot of things going on there, but we plan to make a bit of a community of people interested in developing and using this hyperboloidal approach. And so if you want to check it out, feel free. And thank you very much for your attention, and I'll be happy to take any questions you may have.
When you work with the conformal compactification approach,
Why?
since you don't get the physical metric in the end, don't you lose information?
Well, you know how you, so it's the rescale, you know how you do the rescaling, you can undo that rescaling if you want. So you're not really losing information, again, because you can undo the rescaling if you wish so. Because in the end, the signals, they'll be exactly the same signals you would get if you were evolving in the physical space-time. Only with this trick, you can get those signals in finite time. But you don't have to wait infinitely long for them to reach functional infinity. Because the signals themselves are the same.
Yes, we need to know the it's conformal.
Yes, that's right. The angles don't change. Yeah, and also the compactification you perform is so that it maintains that. The time slices and the compactification on those. The first one is. This one maybe? The collapse one or the other one? Well,
When I saw after interacting
yeah, this is a bit of an older simulation. So in this case, in this specific case, I suspect there may be some numerical artifacts happening a bit at the origin. Like it would possibly look smoother, maybe with a slightly better treatment of the origin. Also have to say this is a bit of an older simulation, so I'm not going to really work on improving that. Also, the origin is not our real world here. But yeah, I mean, you could get this, looking nicer. Yeah, so I think partly to make art topic is not something.
How long does the simulation take?
It was spherical symmetry from seconds to hours, depends on the resolution you want. If you want to do so for the test I'm performing now in 3D, if you want high resolution, that can take 1, 2, 3 days. Like some of the students were performing simulations with high resolution, and it took them, they got to the 3-day limit of that as well. But if you just try things out quickly, it can just take minutes or even hours. I mean, again, this is low resolution and it's just simple scenarios. If you wanted to do a binary, then that would still take me. I would expect that with this approach, we should be able to be faster than current binary simulations, but still it would take some time because of the percent resolution you want.
And how important is the 3D versus like 2D, for example?
Well, I mean, you can only do a binary in 3D. If you are just happy to, something we could do as an intermediate step is just consider axis symmetry and do a head-on collision, for instance. That's already quite a big thing. But indeed, you want a binary in 3D. Because those are the signals that we expect to receive from the interferometers.
I'm seeing the site.
Yep.
Just start because
Yeah, no, I say it's under construction. It's under construction. Yeah, but if you see, we're gonna have we plan to have a meeting in summer, in the events.
yeah, events, one event.
Wow, come on! I mean, it takes some time to get things
People,
going.
for people.
And those people are the
About
organizers.
is half a paragraph.
We will discuss it. I will discuss this on the next meeting we have.
There are two
Articles.
things. Minimal gauge and how to block and rule by.
Yeah,
Okay,
working.
it's just a start.
Indeed. It's, up to a great one, hopefully. So, any what about the question?
The last problem.
Oh yeah.
So do you have any idea?
I'm looking at it right now. Well, I'm going to look at it as soon as I get it back into the office. I was actually considering the different subsystems you can take of the Einstein equations to see. I suspect that maybe due to the way that the slicing condition deals with the fictional infinity. That's one guess. I still have to find out if that's correct or not. Because the wave equation is working fine. It converges well enough, while the Einstein equations do not. It can even be due to the gauge conditions. But I mean, I have to confirm that's the case. I'm sorry. No, because it's just a gauge wave. So basically, it's a participation in the gauge that still satisfies the constraints. So it's just gauge dynamics, but I mean, it's still a test for the code. The next, the previous one. This one. Yeah, sorry. Yeah. This one? Yeah.
But of course, it's like some different possibilities already going from the recent time.
That's also something.
There's something coming from infinity. That's what causes the problem.
I'm not sure that's what caused the problem, but I was yesterday comparing with my numerical relativity, the spherically symmetric code and this one, and there's a similar effect going on there. That's why I suspect it's something at the continuum level, in the way that the gauge conditions treat fictional infinity, but I have to understand it.
Okay. Thanks very much again.
Thank you.
If you enjoyed the video, like and subscribe.